Last week, Andreas Kling, the creator of the Ladybird web browser, used AI coding agents to translate 25,000 lines of C++ into Rust in 2 weeks. The code passed 52,000 conformance tests. 0 regressions. 0 performance loss. That same week, a separate developer used AI agents to write a FreeBSD kernel-level Wi-Fi driver from scratch, with almost no human-written code. These are not toy demos. One is a JavaScript engine inside a real browser. The other talks directly to Broadcom wireless hardware. Let's get into it. Ladybird is an independent, open-source web browser being built from scratch. No Chromium, no WebKit, no Gecko underneath. It's one of the most ambitious projects in open-source software right now, led by Andreas Kling, a former Apple WebKit engineer. The project is targeting an alpha release in 2026 on Linux and macOS, with a stable public release planned for 2028. For the past couple of years, the Ladybird team has been searching for a memory-safe language to eventually replace C++ in their codebase. They tried Swift first. Kling actually announced the Swift direction back in 2024, but the C++ interoperability never worked well enough, and Swift's platform support outside the Apple ecosystem was too limited. So they recently closed that chapter, literally closing their GitHub issue titled Swift 6.0 blockers and turned to Rust. Now when they first evaluated Rust in 2024, they rejected it. Rust's ownership model doesn't naturally fit the deep inheritance hierarchies and garbage collection patterns baked into the web platform's object model. But after a year of limited progress with Swift, pragmatism won. Rust has a massive ecosystem, strong safety guarantees, and a contributor pool that already knows the language. The first component they ported was lib.js, Ladybird's JavaScript engine, specifically the lexer, the parser, the abstract syntax tree, and the bytecode generator. These subsystems are relatively self-contained and, crucially, have excellent test coverage through Test 262, the standard JavaScript conformance suite. Kling used Claude Code and Codex to perform the translation. He was explicit that this was human-directed work. He chose what to port, in what order, and what the Rust output should look like. He used hundreds of small prompts, steering the AI agents step by step. After the initial translation, he ran multiple adversarial review passes, using different AI models to scan for mistakes and bad patterns. The result, roughly 25,000 lines of Rust code, completed in about 2 weeks. That same work, done manually, would have taken months. The translated code passed over 52,000 Test 262 tests, and around 12,000 Ladybird-specific regression tests, with 0 failures. No performance regressions on any tracked JavaScript benchmark. They even ran a lockstep mode, browsing the web with both the C++ and Rust pipelines running simultaneously, and verified identical output for every piece of JavaScript that passed through. The reason this story landed so hard in the developer community is that it answers a question a lot of people have been dancing around: can AI coding agents handle genuinely serious engineering work? This is a browser engine. It has to parse every weird corner of JavaScript correctly. The test suite isn't a handful of unit tests. It's 52,000 conformance checks, plus 12,000 regression tests. The margin for error is essentially 0. And Kling didn't just dump the C++ into a prompt and hit enter. He directed the agents through hundreds of iterations, made architectural decisions, ran adversarial reviews. The AI did the translation labor. The human did the engineering judgment. Simon Willison called it a really interesting case study of advanced, sophisticated use of coding agents for ambitious coding projects with critical code. That framing matters. This is expert-directed agentic coding. A senior engineer with deep knowledge of the codebase used AI to multiply his output by an order of magnitude on a task with strict correctness requirements. For anyone building software today, the implication is concrete. Large-scale code translation, the kind of migration project that companies budget quarters for, can now be done in weeks by a skilled engineer with the right AI tools. The ceiling for what one person can accomplish just moved dramatically. Kling was clear that this isn't a full rewrite. C++ remains the primary development language for Ladybird, and Rust porting will run as a parallel effort over a long time frame. The current Rust code still reads like translated C++ intentionally, to maintain byte-for-byte compatibility with the original pipeline. Once they're confident enough to retire the C++ version of lib.js, they'll refactor toward idiomatic rust. Watch for whether this incremental approach becomes a template other large C++ projects follow. So that's AI agents translating 25,000 lines of browser engine code in 2 weeks. Impressive, but at least translation has a clear source and target. The next story goes further. A developer pointed AI agents at a problem where no target code existed at all, and asked them to write a kernel-level hardware driver from scratch. Vladimir Varankin is a developer. He works at Grafana Labs according to his LinkedIn, who had a 2016 MacBook Pro collecting dust in a cabinet. The laptop had the infamous FlexGates display cable issue, but it still worked. He wanted to repurpose it as a machine to experiment with FreeBSD. One problem: the 2016 MacBook Pro uses a Broadcom BCM 4350 Wi-Fi chip, and FreeBSD has no native driver for it. The standard workaround on FreeBSD forums is to run something called Wi-Fi Box, basically a tiny Linux virtual machine that handles Wi-Fi through Linux's BrexMF Mac driver via PCI pass-through. Functional, but inelegant. Varankin's idea was to use AI agents to build a native FreeBSD driver instead. His first attempt was straightforward. He cloned the Linux BrexMF Mac source code and asked Claude Code to adapt it for FreeBSD, using Intel's EL Wi-Fi driver as a reference for how FreeBSD kernel modules are structured. The module compiled. It even looked promising at first. Then reality hit. The kernel panicked. Repeatedly. The AI agent kept adding compatibility shims and wrappers, the diff ballooned in size, and after multiple sessions, the driver still wasn't close to working. The brute force porting approach had failed. That's when Varankin changed strategy entirely. Inspired by Armin Ronacker's post about building a game with Claude Opus and the Pi agent, he scrapped everything and started fresh. Instead of porting code, he first asked the AI to write a detailed technical specification of how the BrexMF Mac driver works, specifically for the BCM 4350 chip. How does it load firmware? How does it communicate over PCI? What's the protocol sequence for association and authentication? With that spec in hand, he started a brand new project. No existing code, just the spec. He told the Pi agent they were building a FreeBSD driver for the BCM 4350 from scratch, and asked it to raise decision points before writing code. The agent came back with architectural questions. Should the driver live in the kernel source tree? Should it depend on Linux KPI? What are the high-level milestones? Varankin had the agent document every decision in the project's docs, and reference them in an agents.md file, so future sessions would maintain context. Over many coding sessions with the Claude Opus family of models through the Pi agent, the driver took shape. When the code crashed or hung his test VM, Varankin would fork a Pi session, have the agent investigate the crash, document the root cause, and record it for the agent's future self before attempting a fix. The result: a working FreeBSD kernel module for the BCM 4350. Wi-Fi scanning, 2.4 and 5 GHz connectivity. WPA2 authentication, all functional. Varankin says he didn't write a single line of the code himself. The source is public on GitHub. He's clear that it's not production ready. There are known stability issues, but it connects to Wi-Fi and it works. Kernel driver development is one of the hardest domains in software engineering. You're writing code that runs in ring 0, talking directly to hardware through register reads and firmware blobs, with no safety net. A bug doesn't throw an exception. It panics the entire machine. Historically, writing a new kernel driver requires deep expertise in the target operating system's internals. The hardware vendor's documentation, which is often incomplete or non-existent for Broadcom chips, and weeks or months of painstaking debugging. Varankin did it across multiple AI coding sessions with minimal hands-on keyboard time. He provided the direction, the decisions, and the debugging context. The agents wrote the C. The strategic insight in his approach is worth paying attention to. The straight port failed, but when he had the AI generate a spec first, and then write code from the spec, it worked. That two-phase pattern, understand first then build, may turn out to be a reusable playbook for AI-assisted systems programming. Driver availability is the single biggest factor determining whether a niche operating system can run on real hardware. The gap between Linux and the BSDs has been widening for years precisely because nobody has the bandwidth to write and maintain drivers for every chipset. If AI agents can close that gap, the implications go well beyond one MacBook's Wi-Fi. Varankin plans to keep tasking the AI agent with fixing the remaining stability issues. The driver currently only supports one specific chip, the BCM 4350. But Broadcom's full Mac chipsets power Raspberry Pi boards, Apple hardware, and millions of laptops. If this approach generalizes, it could unlock native FreeBSD Wi-Fi support across a much broader range of hardware. Meanwhile, FreeBSD itself has been developing a policy on AI-generated code contributions, so watch how the project's governance handles this kind of work. 6 months ago, the serious question was whether AI coding agents could do anything beyond autocomplete and boilerplate. Today they're translating JavaScript engines and writing kernel driver. The rate at which the boundary of what AI agents can build is expanding should change how every software team plans their next quarter. If you want to stay on top of these developments, subscribe. We cover AI and tech news daily. See you in the next one.